everyone. Welcome to session 6 Control Engineering for 7th semester. In previous session, we have discussed basic concept of body plot. So, what is the structure of body plot? Then, what are the advantages of body plot? Then, we discussed about the frequency specifications. So, in that, we have discussed gain margin, phase margin, gain crossover frequency, and phase crossover frequency. As we know that the Bode plot has two subplots. So one is magnitude plot, another one is phase plot. So x-axis is common for both magnitude plot and phase plot. So that is non-linear scale. That is log omega. So omega can be varied from 0 to infinity. So that's why we use x-axis is non-linear scale. In magnitude plot, y-axis is magnitude, that is in decibel, that is 20 log modulus of uh, k. We have to convert it into decibels. Then phase angle, so y-axis is, that is phase angle in degrees. So in this session we are going to discuss the what are the steps involved to construct the Bode plot, and one worked example, one numerical problem. So these are the steps for solving Bode plot. Bring the given g of s transfer function into standard time constant form. The first step is, so the given transfer function g of s into h of s. H of s is unity, so that has to be converted into, okay, standard time constant form. Then second one, replace all s by j omega to get frequency domain transfer function. The second step, so once you convert standard time constant form, so coming to second steps, so we have to convert s domain to frequency domain by substituting s is equal to j omega. Then another step, prepare a list of standard factors present in the given transfer function. Identify the what are the transfer function. So what is the gain factor? How many poles at zeros? How many zeros at how many poles at origin? How many zeros at origin? Then how many first order zeros? How many first order poles? Second order pole, like that. You have to identify the factors. Then prepare a table of factors. That means we are finding the for corner frequency in the steps. Then next step, prepare a table for magnitude. This table helps you to plot the magnitude curve easily and accurately. For each vector, we are finding the resultant magnitude and corner frequency, where it starts and where it ends. Then another step, choose suitable y and x scale for magnitude plot. Draw line of 20 log k dB. Draw a line of resultant slope corresponding factor from starting point to corner frequency, that is end point. So as we know that x-axis is logarithmic scale. We use logarithmic scale, that is log omega. So why we use logarithmic? We can accommodate large range of frequency, that is 0 to infinity, and also we can expand the small range frequency. That's why logarithmic scales are used in x-axis. Select suitably, then draw a line 20 log k. So that is in decibels, the y-axis in decibels, so that has to be in dB. So, okay, how to convert dB, that is 20 log k. Then another step, write phase angle equation corresponding to phase of the each factor present. Here we have to find out for each factor phase angle. Okay, uh, that phase angle we can calculate tan inverse of imaginary part by real. So once you find out the equation for phase angle, then prepare the phase angle table and obtain the table for omega and resultant phase angle for actual calibration. Then, depending upon the uh, largest frequency term, choose the starting point of log scale, plot the point as per phase angle table, and draw smooth curve obtaining necessary phase angle for each value of omega. So you will get a resultant magnitude or resultant phase angle. Then you have to plot. Then these points are joined by smooth curve. Whereas in magnitude, the resultant magnitude is straight line. Here phase plot, the resultant phase plot is smooth curve. Then so once you complete that phase plot as well as magnitude plot, then we have to calculate the gain margin and phase margin. Then gain margin calculation. From phase resultant curve, find omega where phase curve crosses minus 180-degree line. This is called phase crossover frequency, that is omega Pc. Draw the straight line from omega Pc is equal to omega towards magnitude plot till intersect the magnitude curve. Call this point as G. The difference between 0 dB line and magnitude corresponding to G is gain margin. Okay, here we can understand clearly. So this is the resultant phase curve. Resultant phase curve where it crosses minus 180 degree. Here it crosses the minus 180 degree line. Draw a vertical line towards phase plot. I mean magnitude plot. Then the distance measured from this point, 0 dB line and resultant magnitude curve. So this is called as the gain margin. Now you can see here. So this is the phase plot where it crosses minus 180 degree. Draw a vertical line. Then the distance measured from this point. Okay, 0 dB line to resultant curve, resultant magnitude. This distance it is called from ear to ear. So that is called as the gain margin. Now let's show it after all. Okay, from this point to this point, it is called as the gain margin. So here also from here to here, it is called as the gain margin. Okay. Then coming to how to calculate the phase margin. From magnitude resultant curve, find where resultant crosses 0 dB. This is gain crossover frequency. Draw this right line from omega is equal to omega Gc, that is gain crossover frequency downward till intersect the phase curve called at point as P. The distance point between point P and minus 180 degree line is called phase margin. Okay, go back to previous slide. Now you can see here. So this is the resultant magnitude where it crosses 0 dB line. Here it crosses the 0 dB line. Draw a vertical line. Draw a vertical line downwards. That corresponding frequency it is called gain crossover frequency. Then the distance measured from here to here, that is phase margin. Distance measured from this point minus 180 degree to this one till the phase point. This is called phase margin. If both gain margin and phase margin are positive, then the system is stable. That is, gain crossover frequency it is less than phase crossover frequency. Otherwise, it is unstable. Okay. So by knowing the gain margin and phase margin and gain crossover frequency, phase crossover frequency, we can identify that the system is stable or unstable. Now you can see here. So this one gain margin is positive. Here it is positive. The phase margin here it is positive. If gain margin and phase margin both are positive, then the system is said to be stable, or else this is gain crossover frequency. This is phase crossover frequency. Gain crossover frequency it is less than phase crossover frequency, then the system is said to be stable. So here it is stable system. Now you can see here gain margin above this line it is negative gain margin. The phase margin below this line is negative phase margin. Here it is positive, here it is positive. Here it is negative gain margin, here negative phase margin. Both gain margin and phase margins are negative, then the system is said to be unstable, or else gain crossover frequency it is greater than phase crossover frequency, then the system is said to be unstable. Then summary of Bode plots and phase plot. Constant K, okay, we have to convert this into magnitude, that is in decibels. 20 log modulus of K. So whatever the K value, that has to be converted into decibels. For that 20 log base 10 modulus K. Then phase angle. Phase angle is 0 for A is greater than 0, or phase angle is minus 180 degree for K is less than 0. Pole, poles at origin 1 by j omega, 1 by j omega power of n. Then what is this value? Minus 20 into n dB per decade. Suppose one pole at origin, then its value is minus 20 dB per decade. Suppose two pole at origin, then it is minus 40 dB per decade, so on. Then phase angle is plus 90. Sorry, minus 90. Then coming to 0 at origin, j omega power of n. What is the value of the slope in magnitude? That value is plus 20 into n dB per decade. Suppose we have a 1 0 at origin, then its value is 20 dB per decade. Then 2 0 at origin, its value is plus 40 dB per decade. It goes on like that. Then its value, phase angle value is plus 90 into n degree. First order pole 1 by 1 plus j omega by p1. Slope line 0 dB per decade for omega is less than p1. Minus 20 dB per decade omega is greater than p1. Then phase angle. How to calculate the phase angle? Minus tan inverse of omega by p1. That means imaginary part is omega by p1, real part is 1. So it is minus tan inverse of omega by p1. Then first order 0, slope is 0 dB per decade for omega is less than z1 plus 20 dB per decade omega is greater than z1. Then phase plot plus tan inverse of omega by z1. Imaginary part by real part. So tan inverse of omega by z1 by n 1. So this will be plus tan inverse of omega by z1. Then second order pole 1 by 1 plus 2 j theta omega by omega n minus omega square by omega n square. Then the slope value is, or line slopes are 0 dB per decade for omega is less than omega n, minus 40 dB per decade for omega is greater than omega n. Error correction for omega is equal to omega as per the zeta. Then phase plot, uh, phase angle. How do you calculate the phase angle? Phase angle is equal to minus tan inverse of 2 zeta omega by omega n divided by 1 minus omega square by omega n square. That means, so imaginary part is 2 zeta omega by omega n. Here it is imaginary part. Real part is 1 minus omega square by omega n square. Then second order 0, 1 plus 2 j zeta omega by omega n minus omega square by omega n square. Line strokes are 0 dB per decade for omega is less than omega n plus 40. Here it is minus, here it is minus, here it is plus dB per decade for omega is greater than omega n. Then phase angle plot plus tan inverse of imaginary part is 2j, I mean 2 zeta omega by omega n divided by 1 minus omega square by omega n square. So, okay, that is the summary of basic summary introduction of the body plot. Coming to numerical example, the given transfer function is given g of s is equal to 40 into s by 5 divided by s into s plus 10 into s plus 2. Draw the body plot, find gain margin and phase margin. Okay, so you have to follow the steps. First, check whether the given transfer function g of s value is standard time constant form or not. Bring the it is not in standard time constant form. So bring the standard time constant form. So g of s is equal to 40 into 5, 1 plus s by 5 divided by s into 10, 1 plus s by 10 into 2 into 1 plus s by 2. If we simplify this, so the given transfer function in standard time constant form is equal to 10 into 1 plus s by 5 divided by s into 1 plus s by 10 into 1 plus s by 2. Convert. So this is not in standard time constant form. So bring it to standard time constant form here. Then second step, convert S domain to frequency domain by substituting S is equal to J omega. So wherever S is there, convert that into uh, J omega. So G of J omega is equal to 10 into 1 plus J omega by 5 divided by J omega 1 plus J omega by 10 into 1 plus J omega by 2. Then identify the factors. Then third step, the, uh, identify the factor. How many factors are there? 5 factors. Constant K, then one pole at origin, then we have sim first order pole, then first order 0, another first order pole. K is equal to 10 constant, then 1 by j omega pole at origin, then first order pole is 1 by 1 plus j omega by 2. Then we have to find out the corner frequency. Corner frequency is reciprocal of this, so that is 2 radian per second. Then you take first order 0, this term. Then you have to find out the corner frequency reciprocal of this, that is 5 radian per second. Then fifth factor 1 by 1 plus j omega by 10. Then the corner frequency is 10 radian per second. For this transfer function, we have a three corner frequency 2 radian per second, 5 radian per second, 10 radian per second. Then we have to prepare the step 4. We have to prepare the magnitude curve and phase curve. The constant 10, okay, so that has to be converted into decibel. 20 log base 10 modulus of 10. So that value is 20 dB. Then phase curve is, phase angle is 0. Then pole at origin. Magnitude curve minus 20 dB per decade. Slope is passing through. Omega is equal to 1, 0 dB. Then phase angle is minus 90 degree. First order pole 1 by 1 plus j omega by 2. That value is 0 dB per decade for omega is less than 2 radian per second, minus 20 dB per decade for omega is greater than 2. Then phase angle minus tan inverse of omega by 2. That is imaginary part by real part. Here imaginary part is omega by 2, real part is 1. Then it is minus tan inverse of omega by 2. Then you take the first order 0, 1 plus j omega by 5. Then magnitude curve 0 dB per decade for omega is less than 5 plus 20 dB per decade omega is greater than 5. Then phase angle is plus tan inverse of omega by 5, reciprocal of this imaginary part, imaginary part by real part. Then fifth factor, first order pole 1 by 1 plus j omega by 10. Magnitude curve 0 dB per decade, omega is less than 10. Minus 20 dB per decade, omega is greater than. Then phase angle is minus tan inverse of omega by 10. So imaginary part by real part, tan inverse of omega by 10 divided by 1. So that will be minus tan inverse of omega by 10. Then we have to, step number 5, we have to plot the magnitude table for to construct the magnitude plot. You take the select the factors. Okay. Uh, K values that is initially we have considered that is 20 dB. Then we have a one pole at origin. The resultant slope is minus 20 dB per decade where it starts, that is 0.1 radian per second where it ends. Next corner frequency, that next corner frequency is 2 radian per second. 1 by, now you take another pole 1 by 1 plus j omega by 2. Here our resultant slope is, previous resultant slope is minus 20. For this resultant slope is minus 20, minus 20, minus 20, minus 40 dB per decade. Where it starts, where it starts with the 2 radian, ends with the next corner frequency 2 and 5. Then you take the first order 0, 1 plus j omega by 5. Previous resultant slope is minus 40. For this is plus 20. Minus 40 plus 20, minus 20 dB per decade. Then where it start? 5. Then ends, it is 10, 10 radian per second. Then you take the uh, fifth factor 1 by 1 plus j omega by 10. That previous resultant slope is minus 20. For this is minus 20, minus 20 and minus 20, minus 40 dB per decade. Where it starts, that slope starts at 10 radian per second and ends at infinity. Then phase angle equation, one pole at origin, the phase angle is minus 90 degree. For this pole, it is minus tan inverse of omega by 2. Then 1 by j omega by 5 plus tan inverse of omega by 5. Then another factor 1 by 1 plus j omega by 10. Phase angle is minus tan inverse of omega by 10. Then resultant magnitude summation of all. For this is for pole at origin. Then this is for simple pole. Then this is for first order 0. This is for uh, first order pole, another pole. Okay, then prepare the angle, phase angle table for okay. So this is omega, one pole at origin. this is one first order pole, first order 0, first order pole. So select omega value. Omega value is equal to 1. So this is minus 90 always. Then substitute omega value is equal to zero point 0.1. So this will be minus 2.86 degree. Then if you substitute omega value is equal to here plus 1.14 degree. Then omega value is equal to this one. So this value is minus 0.57 degree. Then summation of these four, so that will be minus 92.29 degree. Then for zero point 0.5, if you substitute corresponding value, the resultant phase angle is minus 101.18 degree. Then for 1, this is minus 110.9 degree. Then for 5, it is minus 139.7 degree. Then for 10, it is 150.2 degree. Like that, for 1000, the resultant phase angle is minus 179.5 degree. So once you tabulate phase angle as well as the magnitude, and then you will have to go for the construction of the magnitude plot as well as the phase angle. So this is the semi-log sheet. So x-axis is non-linear scale, y-axis is linear scale. Why we select the x-axis is non-linear scale? Because omega value is varied from 0 to infinity. So it is difficult to accommodate in linear scale. So that's why we use non-linear scale in XC. Okay. So y-axis is linear. Okay. So here it is decibel. Here it start with the omega value is equal to zero point 0.1. Here it is decade from year to year. Okay. From this point to this point, we call it as a decade. 1 decade, then 2 decade, then here it is 3 decade, 4 decade, and 5 decade, like that. Okay. So here it start with the 0.1. Here it is 1. Then here it is 10, 100, 1000, 10,000, like that. So coming to magnitude plot. Okay, magnitude plot. You take the suitable scale for this. Then draw a line, 0 dB line. So that is the reference line, 0 dB line, 20, 40, 60, like that. Then you have to mark the initial magnitude. So initial magnitude will be, so K in dB, we have to convert it into decibel. That is 20 log K modulus K plus pole or 0. Okay, in our transfer function, we have a 1 pole at 0, 0. 20 dB plus per pole is 20. 40 dB, initial magnitude is 40 dB. Then initial magnitude is 40 dB. Then we have to consider the factors. Okay, so we have to consider the factors. Go back to previous slide. Okay, for slope, resultant slope. Okay, now 1 pole at origin. So what is the resultant? Minus 20 dB per decade. Where it starts, starting point is 0.1 radian per second, then ends at 2 radian per second. Okay, now here minus 20 dB per decade, 1 pole at origin. So it is minus 20 per decade. Per decade means year. Okay, so from year to year we need to join, then it has to be extended. Next corner frequency, what is the next corner frequency? That is 2. Okay, start with the uh, 0.1 per decade, then it ends with the next corner frequency, that is 2 radian per second. Then coming to another slope, that is 1 pole, a first order pole at this one. Okay, Now we can select the resultant slope is minus 40 dB per decade. Where starting point is 2 radian per second, ends is 5 radian per second. From this point, okay, from this point minus 40 dB, minus 40 dB downwards, okay, minus 40 dB downwards. Then per decade, 2 to next 2. We are supposed to join from year to year, but we have a corner frequency, another corner frequency at 5. Then it has to be extended till year only. It has to be drawn year only. Then you have to take another first order 0. So that value, okay, first order 0, that value of the slope is minus 20 dB per decade. Where it start with the 5 and ends with the 10 radians. From this point, from this point, we have to, this line has to be minus 20 dB per decade, minus 20 dB. Okay, let us assume this is minus 20 downwards per decade. Okay, 5 to, I mean 5 to 5. Then we have to join year to year, but corner frequencies at 10. Then join from year to year. Then for another pole, that resultant magnitude is minus 40. Where it start at 10 and ends at infinity. 10 and infinity. Okay, then its value is minus 40. From here downwards, then 40, then extended simply. Okay, it has to extend it till infinity. So this is the resultant magnitude. Resultant magnitude. Then phase angle plot. Then for each corresponding x-axis omega value, then resultant phase angle is this one. So we have to plot for point 1, it is minus 92.29 degree. Then for point 5, minus 101.18 degree, like that. For 500, it is minus 179.1 degree. Like that we have to plot. Then for point 1, that one. For point 5, then these points are joined by smooth curve. The resultant magnitude is straight line. So this is smooth curve. Friends, smooth curve. Then once you complete, this is body plot, this is phase angle plot. So we have to find out the gain margin as well as the phase margin. Okay. Now you take the resultant magnitude here. Resultant magnitude where it crosses 0 dB line. Now here it crosses the 0 dB line. Draw a line, vertical line downwards. Okay. Then so this line minus 180 degree line and resultant phase plot, the distance measured from year to year, this is called as the phase margin. So if you count this, so this value is 42 degree. Then the sign convention, it is positive phase margin. Then it is for you, you have to find out the gain margin. Gain margin, so now you consider the phase plot where it crosses minus 180 degree line. Here it crosses the minus 180 degree line. Draw the vertical line towards magnitude plot. The distance measured from 0 dB line, this 0 dB line, and resultant magnitude at this point. So from year to year, we call it as the gain margin. If you count this, so this will be 84 dB. Then sign convention, it is positive. Then gain crossover frequency. So this is phase crossover frequency. Then what is the stability of the system? gain margin. So gain margin and phase margin are positive, then the system is stable, or else the gain crossover frequency. Gain for crossover frequency, that is 4.5 radian per second. Phase crossover frequency, that is 1000 radian per. Gain crossover frequency is less than phase crossover frequency, then the system is said to be stable. Then you have to tabulate this one, gain margin and phase margin, gain crossover frequency and phase crossover frequency. Then we have to comment on the stability. The stability is the stability of the system is, I mean, for this transfer function, it is completely stable. Okay.